Hey everyone, and welcome back. Today, we're looking at mathematical proofs, a fundamental skill in mathematics, and definitely something you'll encounter in IB math. Now, for this topic, there is a bit of a difference between SL and HL. We'll start with concepts relevant for everyone, and then we'll clearly signal when we move into HL-only territory. First up, what even is a proof? In simple terms, a proof is a logical argument that demonstrates, beyond any doubt, that a mathematical statement is true. It's about certainty rather than guessing or observing patterns. This brings us to our first key idea: examples versus counterexamples. Imagine someone claims that the formula n squared plus n plus 41 always produces a prime number for any positive integer n. You could try n is equal to 1, which gives you 1 plus 1 plus 41, which is 43, and that is prime. Then n is equal to 2, giving us 4 plus 2 plus 41 is equal to 47, also prime. N is equal to 3, yielding 9 plus 3 plus 41 is equal to 53, prime again. You could try this for many values: n is equal to 10, n is equal to 20, even n is equal to 30, and you'd keep getting primes. Does this prove the statement is always true? No. No matter how many examples you provide that work, you still haven't shown it works for all possible values. An example can illustrate a statement, and with that regard is very useful, but it can't prove a general rule. But what if you want to disprove a statement? Let's test n is equal to 40. We get 40 squared plus 40 plus 41 is equal to 1600 plus 40 plus 41. That's 1681. Now 1681 happens to be 41 times 41, and is therefore definitely not prime. This single instance, n is equal to 40, where the statement fails, is called a counterexample. And unlike examples for proving, a single counterexample is enough to disprove a statement entirely. If a statement claims something is true for all cases, finding just one case where it's false breaks the whole claim. Okay, so if examples aren't enough to prove something, then how do we do it? One common method, relevant for both SL and HL, is the direct proof. The idea is quite straightforward. If you want to prove a statement of the form if P then Q, written symbolically as P implies Q, you start by assuming P is true, and then use logical steps, definitions, and previously proven facts to show that Q must also be true. A very common type of direct proof you'll do, especially in SL, involves proving identities or algebraic statements. Often, this takes the form of starting with one side of the equation, usually the more complex side, and manipulating it algebraically until you arrive at the other side. For example, let's prove that a minus b times a plus b is equal to a squared minus b squared. We start with the left-hand side, a minus b times a plus b. Then we expand the brackets. A times a plus b minus b times a plus b is equal to a squared plus ab minus b squared. Since ab is equal to ba, this simplifies to a squared plus ab minus b squared is equal to a squared plus b squared. And look, that's exactly the right-hand side. So we've shown the left-hand side is equal to the right-hand side, and the identity is proven. That's the essence of direct proof, a logical chain from assumption to conclusion. Alright, now we're moving into techniques primarily for HL students. SL folks, you're covered with examples versus counterexamples and direct proofs, but do feel free to learn the rest, they're very interesting. HL students, you'll need these next two as well. First up for HL is proof by contradiction. This one's a bit sneaky, but it's very powerful. Instead of proving a statement A is true directly, we start by assuming that the opposite of A, which we call not A, is true. Then, we follow logical steps just like in a direct proof. If our assumption, not A, leads to something impossible, a contradiction like saying 1 is equal to 0 or that an integer is both even and odd, then our original assumption must have been false. And if not A is false, then the statement A must be true. A classic mathematical example is proving that square root of 2 is irrational. The proof starts by assuming the opposite, square root of 2, is rational. This assumption eventually leads to a contradiction, forcing us to conclude that square root of 2 must be irrational after all. We won't go through the full proof here, but the strategy is key. Assume the opposite, find a contradiction, and conclude that the original statement is true. The final major proof technique, again for HL students primarily, is proof by mathematical induction. This is often used to prove statements about natural numbers, things like formulas for sequences and series or divisibility properties. Imagine an infinitely long staircase. You want to prove that you can reach any step on the staircase. How can you do it without climbing infinitely? Induction gives us a way. It involves two key parts. First off is the base case. First, you prove that you can get onto the first step. This is usually showing the statement is true for n's equal to 1 or sometimes n's equal to 0. Easy enough. Now the second part is the inductive step. This is the clever part. You don't prove that you can reach step k plus 1 directly. Instead, you prove something conditional. If you can reach some arbitrary step, let's call it step k, then you can definitely reach the next step, step k plus 1. You assume our original statement, which we're trying to prove, is true for some n is equal to k. This is called the inductive hypothesis. And you use that assumption to prove the statement is true for n is equal to k plus 1. Now think about what this means. You've shown you can get on step 1 with the base case. And you've shown that if you're on any step k, you can get to step k plus 1, the inductive step. Well, since you can get to step 1, the inductive step means you can get to step 2. And since you can get to step 2, the inductive step means you can get to step 3. Since you can get to step 3, you get the idea. Like dominoes falling, proving the base case and the link between k and k plus 1 proves the statement for all natural numbers n. So the structure is always, first, prove the base case, usually n is equal to 1, then assume the statement holds for n is equal to k, the inductive hypothesis, then using that assumption, prove the statement holds for n is equal to k plus 1, that's the inductive step, and finally, conclude that this statement is true for all n in n, or whatever the relevant set is, by induction. And those are the main proof techniques you'll need for IB Math AA. So to recap, everyone, both SL and HL, needs to understand the difference between examples, which are not a proof, and counterexamples, which are a disproof. You all need to master direct proofs, especially when you're trying to prove an identity by showing that the left-hand side is equal to the right-hand side. And for HL students only, you need to add proof by contradiction, where you assume the opposite and find a contradiction, and proof by induction, which we've just covered, to your toolkit. And that's all for proofs. Next time we'll look at systems of equations. See you then.